Potential due to an electric dipole. Let us consider a pair of equal and opposite point charges placed at a small distance apart. Its moment, known as electric dipole moment, is a vector p having magnitude equal to product of the charge and the distance between the charges. The direction will be pointing from negative charge to positive charge, and we have to calculate the potential at a point on the axis of the dipole. That means first we are calculating at the axis of the dipole. For this, let us calculate the potential due to plus q charge which is placed at B. It is 1 upon 4 pi epsilon naught q upon distance. Here the distance will be r minus L because point B is located at distance r minus L from P. Now let us calculate potential due to minus q charge which is placed at A. It is 1 upon 4 pi epsilon naught minus q upon the distance. Here the distance will be r plus L. Now in order to calculate the resultant potential at P, as potential is a scalar quantity, the resultant will be simply the sum of the above two potentials. When we will calculate the sum, 1 upon 4 pi epsilon naught and q are the common terms, and we can write the rest of the terms in this manner. Simplifying it further, we will get r square minus L square in the denominator. And if we look carefully in the numerator, it is q into 2L, which is electric dipole moment. So I can represent this numerator term as P, electric dipole moment. As this distance r is very large as compared to the length of the dipole, which is small, so we can neglect L square in the denominator and we are left with potential formula as 1 upon 4 pi epsilon naught P upon r square. Now let us calculate potential at equatorial line of dipole. Equatorial line means a line which is passing through the center of the dipole. Let the point charge be placed at point P and its distance from the center of the dipole is represented as r. Now to calculate the potential due to charge plus q which is placed at B, it is 1 upon 4 pi epsilon naught q upon the distance, here it is BP, and the potential due to charge minus q will be represented by 1 upon 4 pi epsilon naught minus q upon the distance, here the distance is AP. But if you look carefully in the figure, the distance BP and AP will be equal to each other. So the resultant potential at P, as it is a scalar quantity, will be the sum of the two, and it will come out to be 0 because BP and AP are equal to each other. See, it shows us that the electric potential is everywhere 0 on the equatorial line of the dipole. Or in other words, we can say that no work is done in moving a charge along this line. No work is done in moving the charge along this line. Now let us calculate potential at any point. For this, consider a point P which is placed at a large distance r from the dipole, on which we have to calculate the electric potential. Let the polar coordinates of P be represented as r theta. Now let us join PB and PA and draw perpendiculars AD and BC on this line OP. Since R is much greater than L, we can write BP is equal to CP. And what will be the value of CP? CP is actually OP minus OC, if you clearly view from the figure. OP is represented as R and OC is calculated by considering this a small triangle. OC will be equal to L cos theta. Similarly, we can calculate AP. AP is equal to DP for large values of R, and this DP is equal to OP plus OD. OP is again R and OD can be calculated by considering this a small triangle. It is L cos theta. Now potential at point P due to charge plus Q, which is present at position B, is equal to 1 upon 4 pi epsilon naught into Q upon the distance. Here it is represented as BP, and BP we have just calculated. It is 1 upon 4 pi epsilon naught Q upon R minus L cos theta. Now potential due to charge minus Q is 1 upon 4 pi epsilon naught Q upon distance. Here it is AP and the charge is minus Q. So it is represented as 1 upon 4 pi epsilon naught into Q upon AP. We have just calculated above. It is R plus L cos theta. So the resultant potential at P, as it is a scalar quantity, it will be V1 plus V2. Adding the above two equations and taking common to simplify it, we are left with R minus L cos theta and R plus L cos theta in the denominator. If we further simplify it, we will get two L cos theta in the numerator, and in the denominator it will become R square minus L square cos square theta. If we look carefully, Q into 2L is nothing but electric dipole moment. So we can write down it as P cos theta upon R square minus L square cos square theta. As R is very large as compared to L, we can neglect L square cos square theta from the denominator. So we are left with a generalized term, that is potential is equal to 1 upon 4 pi epsilon naught P cos theta upon R square. See, we can get all the three cases from here only. If we put theta is equal to 0, we get axial point potential. It will come out to be the same. And if we put theta as 90 degree, then we will get at the equatorial point, that is potential is 0 because cos 90 is 0. Thank you.